I want you to picture something for just a second. Imagine you are looking at a blueprint of a house.
Okay.
You can see the kitchen, the bedroom, the living room, all of it at once. It's flat, it's instant, and everything is right there where it's supposed to be.
Right, yeah. That is what you'd call the God's eye view, the architect's view.
Exactly. Now, imagine you are actually in the house. You're standing right there in the kitchen.
Hmm.
You can't see the bedroom because there's a wall in the way. And more importantly, if someone yells from the living room, it takes a split second for that sound to reach you.
Right, you don't experience the whole house instantly.
Yeah, you experience it locally from where you are standing.
And that, right there, is the fundamental conflict we are unpacking today.
Right.
Because what if I told you that for over a century, physics has been trying to force the universe to fit onto that flat blueprint?
When reality is actually behaving like the person standing in the kitchen.
Exactly. It creates sort of a ghost in the machine, or rather, ghost in the math.
Which is a pretty bold premise. The source material we're diving into today argues that the way we visualize the speed of light, and specifically the famous Michelson-Morley experiment that paved the way for relativity, is basically built on a misunderstanding of how we see.
Yeah, it's a radical reinterpretation. We are going to explore this concept called the light ray standard. And to do it, we really have to ditch the dusty textbooks.
We're bringing in the good analogies.
Right, the sources use some great modern analogies that actually make sense to us now. We're talking about iPhones, anime robots, and a sniper with a very, very difficult shot to make.
I do love a good anime reference in a physics deep dive, but let's start with the basics first. The source material sets up a specific scenario to prove this whole point.
The whiteboard and the iPhone.
Yeah. Can you walk us through that?
Sure. So visualize this with me. We have what the text calls a global coordinate system. Imagine a whiteboard just lying flat on the ground.
Okay, whiteboard on the floor, ground zero.
Right. In math terms, that's our XY plane where the vertical height, the Z-axis, is 0.
Got it. Z equals 0.
Now, take an iPhone 15 camera and suspend it exactly 10 units directly above the whiteboard.
10 feet, 10 meters, whatever. We'll just call them units.
Yeah, just 10 units of distance. So the camera is at Z equals 10. Seems super simple. But this setup creates a battle between two completely different ways of seeing the world. Two different eyes.
The two eyes from the outline. First, you have the God's eye, which we mentioned with the blueprint.
Right. This is the view from outside of real space and time. You could hypothetically say it's looking down from Z equals 30.
The mathematician's eye.
Exactly. If you are the God's eye mathematician, you're looking at the design plan. You know that at time 0, let's call it T equals 0, the whiteboard is at the bottom and the camera is at the top simultaneously.
You see the whole geometry instantly.
You do. This is basically how Isaac Newton looked at the world. Action at a distance. Instant knowledge of where everything is.
Everything happens on the same clock. Tick-tock. The universe just moves forward together.
That's the classical view. But now we have to switch to the iPhone eye.
The physical eye.
The local eye, yeah. This is the physical reality of the sensor. The camera is located at Z equals 10. If something happens on the whiteboard down below at time 0, say, someone draws a red dot, does the iPhone see it at time 0?
No, because light has a speed limit, it has to travel up to the lens.
Precisely. In this thought experiment, just to keep the math really clean, we say the speed of light, C equals 1.
Okay.
Since the camera is 10 units away, the light takes 10 units of time to travel from the board to the lens.
So the iPhone creates a record, photograph, but for the iPhone, that event didn't happen until T equals 10.
Right, even though the God's eye view knows the physical event happened at T equals 0.
So the observer's reality is delayed by the travel time of the light.
And here is the aha moment right out of the gate. The source argues that physics constantly confuses these two views.
We draw our diagrams as if we are the God's eye.
Yes, we draw these diagrams seeing the whole setup at once, but then we try to calculate the physics based on the iPhone eye, which has that built-in delay.
So we're mixing up the map and the territory.
We are mixing up the design plan with the phenomenon. We treat them as if they are happening in the exact same jury that they aren't. And the author argues this confusion is the root of a 100-year misunderstanding in physics.
Because it leads to all sorts of paradoxes when you start talking about relativity and moving objects.
Exactly.
And this gets even wilder when you stop thinking about a single dot on a whiteboard and start thinking about a whole picture. Because the sources bring up this concept of the turret lens next.
Yes, the turret lens.
This is where the anime reference comes in, right? Armored Trooper Vodo AS.
Yeah, the Scope Dog mecha from Vodo Guess. For those who aren't familiar with classic mecha anime, just imagine an old-school cinema camera with a rotating turret on the front.
Like, it has 3 different lenses mounted on a wheel, and you physically spin it to change lenses.
Right. It has a standard lens, maybe a wide angle, and a zoom. You just flip between them.
So let's say I switch from the standard lens with a 90-degree field of view to the wide-angle lens with a 120-degree field of view. How does that change what we were just talking about with time?
It completely changes the geometry of the light path. This is a crucial visualization. Let's think about our iPhone suspended at z equals 10 again.
Okay, looking straight down.
The pixel in the dead center of the photo is capturing light that came from directly below it. That's the shortest possible path.
Straight up and down. Distance is 10, time delay is 10.
Correct. But what about a pixel at the very edge of the photo, especially if you're using that wide-angle lens?
Well, that light didn't come from directly below. It came from way off to the side.
Right. It traveled along the hypotenuse of a triangle.
Oh, right. Basic Pythagorean theorem. The slanted side of a right triangle is always longer than the vertical side.
Exactly. So if the vertical distance to the center is 10, the distance to that edge point might be, say, 14.14 units.
Right.
Or even 20 units, depending on how wide the lens actually is.
And because c equals 1, the speed of light is constant.
That means the light took 14 or 20 units of time to reach the edge pixel, compared to just 10 units for the center pixel.
Wait, let me process that for the listener. So the center of my photo shows me the world as it was 10 seconds ago, but the edge of that exact same photo shows me the world 20 seconds ago.
Yes. A single photograph is not a flat slice of one moment in time. The source calls it a time funnel.
A funnel of time.
It packs different times into a single frame. The center pixel is newer news. The edge pixels are older news.
That is actually kind of disturbing when you think about it. We treat a photograph like it's a perfectly frozen moment, like this is a picture of the party at exactly 8 p.m.
But it's not. It's a mosaic.
Yeah.
It's a gradient at different times. And the source argues that standard physics entirely ignores this time gradient within a single frame.
Because we treat a moving object in a photo as a solid, rigid body.
Right. But in reality, its image is smeared across different times depending on where it sits in the lens.
So if a car is driving through the frame, the front bumper and the back bumper are being recorded at slightly different ages relative to the camera sensor.
Exactly. And the source's point is that when you ignore that funnel effect, you start having to invent complex mechanical explanations to justify why the image looks distorted.
Which sets the stage perfectly for the big action sequence in the deep dive notes, the sniper's dilemma.
Yes.
This is a thought experiment from the sources, and it's where the rubber meets the road, or where the laser meets the mirror, I guess.
This scenario is explicitly designed to show why that classical way of calculating motion, the God's eye math, completely fails in practice.
Okay, set the scene for us.
We have a highly trained sniper stationed at the origin point, 0, 0, 0, in the global coordinate system.
He's sitting perfectly still at the center of the grid, and he has a target.
The target is a mirror. This mirror represents the arm of the Michelson-Morley interferometer, which we'll get to. But for now, just picture a mirror moving along the x-axis.
And it's moving fast.
Very fast. It's moving at 10% the speed of light, 0.1 c.
Okay, so the sniper wants to hit this moving mirror with a laser pulse. He can't just aim at where the mirror is right now. He has to calculate a deflection shot.
Right. It's exactly like a quarterback throwing a pass to a running receiver.
Mm-hmm.
You don't throw the football to where the receiver is when you release the ball. You throw it to where they're going to be when the ball gets there.
You have to lead the target. That's just basic mechanics.
So the sniper does the math using classical physics, the God's eye math on paper. He thinks, okay, the target starts at x equals 0. My laser pulse takes about 10 units of time to travel out there. In that time, the target will move to the right.
And the sources are very specific about the math here. They correct an older assumption and state the sniper calculates the target will be at exactly x equals 11.05.
Right. So he aims his laser at the coordinate 11.05 on the x-axis and 10 on the y-axis. He aims at the empty space where the target should be when the light arrives.
He leads the target. He pulls the trigger.
Yeah. He completely misses. The light does not hit the mirror.
But why? If he knows the exact speed of the mirror and he knows the exact speed of light, why does the classical math fail him?
Because he used classical math space. He treated the scenario like a shadow moving across a flat 2D wall. He didn't account for electromagnetic reality.
Break that down for us. What exactly is electromagnetic reality in this context?
Think about the light leaving the sniper's laser. It expands as a sphere from the exact point of emission, which was 000. Once that light leaves the source, it is completely independent.
It doesn't care about the sniper anymore.
No, it expands outward at c=1 in all directions. It creates a light cone.
A growing bubble of light.
Right. Now, the coordinate the sniper, aimed at 11.05, is a specific physical point in space. But here's the catch. The physical distance from the sniper to that specific point is simply too far for the light to travel in the time allotted.
Wait, so the space-time road doesn't actually reach there yet?
Exactly. The light is fast, but its speed is finite. By the time the mirror gets to that spot, the expanding light sphere hasn't grown big enough to touch it yet.
Wow.
The coordinate 11.05 is what the source calls a ghost location. It perfectly exists in the sniper's linear extrapolation on his paper blueprint, but it is not a valid point on the physical light cone.
There is no space-time road for the light to take to get there to meet the mirror at that exact moment.
So he's shooting at a phantom. He's shooting at a spot that the classical math says exists, but the physical light says, sorry, I can't get there that fast.
That is fascinating. And this perfectly leads into the proposed solution in the text, the marriage of Descartes and Maxwell.
Yes, it sounds like a very intellectual wedding.
It really does. But it's about reconciling the rigid Cartesian grid of Descartes with the expanding electromagnetic fields of Maxwell.
Exactly. The source proposes a new global coordinate system governed by two absolutely unbreakable rules.
Let's lay them out. What's rule number one?
Rule number one is fixed emission. When a flash of light occurs, the center of that expanding light sphere is permanently nailed to the coordinate where it happened in the global grid. It does not move.
Now, this is the part that I think really trips people up. Because if I'm standing on a moving train and I flash a flashlight, I feel like the light is moving with me. Like if I tossed a tennis ball straight up in the air and caught it while the train is moving.
Right, that's our everyday intuition. But the light ray standard says absolutely not. The moment the photon leaves your flashlight, it belongs to the universe. Its center is pinned to the physical track where you were standing at that exact microsecond.
So the train just continues moving through the expanding sphere of light. You leave the center behind.
Yes. And that brings us to rule number two, independent expansion.
Meaning the light sphere expands at c=1 regardless of how fast the train is moving.
It doesn't pick up any extra velocity from the train. It just expands at its own constant rate.
So let's apply this back to the Michelson-Morley experiment, because that was the experiment that tried to find the ether wind and famously failed.
Right. They assumed that the light bouncing back and forth in their instrument would behave like the tennis ball on the train. They thought it would take a diagonal path relative to their moving mirrors.
But the light ray standard argues that is completely false. The light expands from the fixed point of emission in the global field.
Which means the moving mirror on their instrument was actually running away from the light source.
And because of the iPhone eye delay we talked about earlier, the scientists were looking at ghost mirrors.
Yes, ghost mirrors. Because the visual information takes time to travel back to the observer, where they saw the mirror was not where the mirror physically was in the electromagnetic field.
So they were calculating their angles based on a visual echo.
Exactly. They failed to detect the ether wind because the entire geometry of their setup was fundamentally misunderstood. Just like the sniper, they were aiming their math at a ghost position.
Now, usually when someone comes along and says, you know, the pioneers of physics were entirely wrong and the math is broken, it's a fringe theory. But the source material points out that one of the absolute heavy hitters of physics actually got this right.
Hermann Minkowski,
Einstein's teacher.
the man who basically gave us the concept of space-time. The source effectively frames him as the hero of the story here.
Because Minkowski realized that classical space, that flat 2D paper map our sniper was using, just wasn't enough to describe reality.
Right, you can't just pick an x-coordinate and a y-coordinate and say, go there. You also have to check the time budget.
The source says Minkowski unconsciously digitized the truth. What does that mean in this context?
It refers to his famous formula for the invariant interval. The math is s squared equals c t squared minus x squared plus y squared plus z squared.
Okay, we try to keep the heavy math to a minimum for you listening, so let's translate that.
Think of it as a rigid balance sheet. For a ray of light to successfully connect 2 points in the universe, the distance in time, that's the CT part, must be exactly equal to the physical distance in space, the XYZ part.
If you subtract one from the other, The ledger has to balance perfectly to zero.
Exactly. The travel time budget has to exactly match the destination distance cost.
So let's bring our sniper back in. He aimed at x equals 11.05.
Right. If you take that coordinate, 11.05, and plug it into Minkowski's balance sheet formula, it does not equal zero.
The space cost is too high for the time budget.
Yes, it mathematically proves that the light physically cannot hit that target. Minkowski understood something profound. You cannot treat time as just a separate clock ticking on the wall while objects move around in space.
Distance in space is distance in time.
They are the exact same thing to a photon. When our iPhone camera looks at the whiteboard 10 units below, it isn't just looking 10 units down in space. It is looking 10 units back in time.
This is the massive takeaway for me. We are so used to thinking of space and time as two different categories. Space is where things are located, and time is when events happen to them.
But this light ray standard philosophy argues there are just two ways of measuring the exact same separation. Distance in space is distance in time.
So we have to stop pretending we can cleanly separate them.
We have to stop treating light as if it's just a fast object moving through a fixed reference frame, like a really fast train on a track. Instead, light is the reference frame.
The global coordinate system is defined by the light itself. The light sets the rules.
When a flash occurs, that exact point is the universal anchor. Everything else, the planets, the moving trains, the mirrors, our iPhones, all of it is just scrambling around relative to that fixed flash.
And if we anchor our physics there, a lot of the confusing paradoxes just evaporate.
We don't need to invent explanations for why physical lengths magically contract or why mechanical clocks slow down. We just need to acknowledge that our local eyes are looking at ghosts through a time funnel.
It's a huge perspective shift. It feels almost philosophical, but it's entirely grounded in geometry.
It really is about cleaning up the map so it finally matches the physical territory.
Okay, so let's bring this down to earth for you listening. Or down to our pockets, really, since we started with an iPhone.
Yeah, let's do that.
What does all this mean for us, practically speaking? I mean, I'm definitely not calculating any laser sniper shots at 10% the speed of light.
No, probably not.
Yeah.
But you are constantly navigating a world that is entirely defined by light. And understanding this changes how you understand the concept of now.
Right.
We walk around all day assuming we share a universal now with everyone else in the room. But we don't.
Because of the travel delay.
Because of the delay.
Right.
We are each trapped in our own little bubble of iPhone eye perception. We never actually see the global grid. We only ever experience the delayed signals that finally reach our specific coordinates.
Which brings me right back to that time mosaic idea. I really can't get that visual out of my head.
The very powerful image.
So, here is a final provocative thought for everyone listening to mull over. Next time you pull out your phone to take a selfie with a friend, or honestly, even just look at yourself in the bathroom mirror in the morning, remember the light ray standard. You aren't capturing a single moment in time.
No, you are stitching together a flat collection of delayed signals from the past.
The light reflecting off the tip of your nose actually reached the camera lens slightly faster than the light reflecting off your ears.
Technically speaking, yes. The hypotenuse is longer. So your nose is literally younger than your ears in every single photograph you've ever taken.
You are a time traveler in your own JPEG.
A mosaic of the past, completely masquerading as the present.
That is beautiful and slightly terrifying to think about. But I want to thank the God's Eye and the iPhone Eye for giving us these two very different but very necessary perspectives today.
It was a real pleasure to unpack all this geometry with you.
And thank you to everyone listening to this deep dive. Keep questioning the map you're using. We'll see you in the future, or, depending on your reference frame, maybe we already have.
Well, that depends entirely on your light cone.
Exactly. See ya.